Hey everyone. All right, this is the final video lesson for this semester. And then on final day, we will just do kind of a wrap up of important problems that we've seen throughout the semester. All right, so this is called the second derivative test. We've seen the first derivative test. So let me remind you, quick review. I could ask you to classify the critical points of a function like this. F of x equals, I'm choosing a very, very, very easy basic one just to get my point across. Okay, so find the critical points and classify them. That's the first derivative test, right? Take the first derivative, which is 6x plus 6, set it equal to 0, x equals negative 1. And then we do the number line, negative 1, f prime of x, and we plug in something bigger than negative 1, like 0, that's a positive. Plug in something less than negative 1, like negative 2, that's a negative, so the graph goes down, and it goes back up, which makes sense because it's a parabola. And this is a relative min. Okay, this whole thing I just did right here was called the first derivative test, where we use the first derivative to determine what type of critical point it is. First derivative test. There's something called the second derivative test, and it does the same thing. So the second derivative test is also used to classify critical points. Here's how it works. Come back to the function. We've already found the first derivative. Find the second derivative. Second derivative is just 6. Do a second derivative number line, or here's the thing, and this one's a little bit of a funny example because the answer is just 6, which means it's always a positive value. But here's the idea. Take your critical point and plug it into the second derivative. The output is still 6. Sometimes it'll be, you'll actually have to work the equation, but in this case, it was just 6. What is this? This is a positive value, which translates into the graph here at x equals negative 1 is concave up because we've got a positive second derivative. Well, if we know it's a critical point, and we know it's concave up because the second derivative was positive, how do you put those two things together? Well, it levels out there, but it's also concave up there, which means it has to be a relative min. Okay, the second derivative test. It's basically saying, look at the second derivative. If the second derivative is positive, then it looks like this. It's a min, relative min. If the second derivative is negative, it's got to go like this, concave down. That's a relative max. At the critical point. It has to be a critical point. If it's not a critical point, then it's just another part of the graph. But this is how you determine if it's a critical point. You can then determine if it's a max or min using the second derivative. So this was called, this process right here was called the second derivative test. Second. Because we used the second derivative and looked at concavity. That's the idea. Why would you use this as opposed to the first derivative test? Sometimes they design problems that tell you what the first and second derivative are, like I did in the homework, and you have no idea what the function looks like, so you can't do the first derivative test. But if I tell you like exactly the values, you can put those things together. So sometimes we'll have specific values, and you'll just have to put the information together. So example 2. Sometimes I'll also do this. There we go. So check it out. I've already given you the first derivative, and then I could ask you to do something like find/classify critical points using the second derivative test. The other thing is, second semester, we're going to do a lot of stuff with the second derivative and using it to talk about concavity. So I'm trying to get you in the mindset that the second derivative really does help us with things about concavity. All right, so let's do this. let's first find the critical points by setting the first derivative equal to 0. So we set it equal to 0. It's already been factored for us, so we set each factor equal to 0. Looks like we have a critical point at 4. Looks like we have a critical point at 1. You could do both sides if you want. 2 critical points. We could do the first derivative test. We're not going to, because the practice today is the second derivative test. So let's come over here and let's find the second derivative. And yeah, I'm using the implicit differentiation notation because that's how I started. But it still just means finding the second derivative. So derivative of the first times the second, product rule, plus derivative of the second times the original first. All right, so let's test each one of these. So in the second derivative, now I'm going to flip back to the old notation. I'm going to plug in 1, and I'm going to plug in 4. Well, when I plug in 1, I get natural log of 1, which is 0, plus, it looks like -3. So that's a negative value. When I plug in 4, I get 0 in the back term and natural log of 4, which is a positive value. So what is that telling me? Negative value means I'm concave down, which means I have a relative max here. In the original function that I can't even find. I don't even know what the original function is. And here I have a concave up situation, so I have a relative min at x equals 4 in the original function that I can't see because all I have is the derivative. If you could figure out kind of what you did on the discussion last time, how to go backwards and find the original function, you could, but you can't. I can because it's a Calc BC topic. We actually figure out how to do that. And second semester, that's kind of, spoiler alert, we're going to be going backwards. I started with the derivative. You tell me about the original function. But we're not doing that right now. All you're doing right now is using the second derivative to classify whether or not these are maxes or mins based on concavity. So concavity is going to become a big deal second semester. A big deal. Concavity. All right. That's pretty much all we're doing. Let's do one more example, and then I'll do, as promised, I forgot to do it last time, I'll give you an AP problem that you can take a look at. So third example, if I tell you that the first, or if I give you this information, if I say f prime of 1 equals 0 and f double prime of 1 equals 0. If I tell you f prime of 1 equals 0, f double prime of 1, let's change the name of this function. Let's call this g. Is equal to 6, and I tell you h prime of, out of the way. And last one, let's say h prime of 5 equals 3, h double prime of 5 equals 0. What do you get from all this information? What's happening at 1? Well, in this first one, this is telling me we have a critical point, and this is telling you it's an inflection point. So all you really know is that it either does this or it does this. It has to level out, and it has to be an inflection point, a change in concavity. But I can't really classify it. It's just a critical point and an inflection point, but well, that means it's a neither, I guess. So I can't classify it. It's one of those neithers where it's an inflection point. Okay, and the second one, if I know this is a positive value and it levels out at 0, meaning it's a critical point, but it's not an inflection point, it's a positive value, that means I'm concave up. So that's the case where I have a relative min at x equals 1 in the original function that I can't see. Finally, this one. What if I tell you it's 3, which means it's increasing, but the second derivative is 0? Well, that's going to have to be this type of thing, where it stops for a second, which means it's an inflection point, not a critical point. It's an inflection point, not a critical point. It's a change in concavity. So it's kind of like when you have the cubic 2, for example. I guess it could be like this without changing. Changes from concave up to concave down. It doesn't have to go vertical. It could just be kind of like this. And actually it can't go vertical because then it would be, the first derivative would be undefined. It has to be more like this. We were concave up, and then we flipped to concave. Or we were concave down, and we flipped to concave up. Okay. So concave down, flip to concave up, from slowing down to speeding up in the increasing direction. Because it was increasing, because this first derivative was positive. All right, so that's the idea of the second derivative test. Homework deals with that idea, and again, second semester, we look a lot at concavity. All right, the other thing I wanted to do quickly, I found a problem that's good, not hard. Just again, we're going to be doing a lot of this stuff, so I'm going to just kind of pick random problems that I think are good to look at. And your call. If you're planning to take the AP test and you want the practice, good, I would. If you're not planning to take the AP test, or you have other things going on and don't want the practice, fine. This is not part of the lesson. This is just an old topic. Okay, so here we go. We have a function where on the graph of f, where's the property that the line tangent has a slope of 1/2. Tangent, it means we want to make a tangent line. So we need to make a tangent line where the slope is 1/2. So to make a tangent line, we need to find the derivative. By the way, I would do this on your own and then check with me. That's always what I'm going to be telling you. Do this on your own and see if you can figure it out yourself. Okay, so let's find the derivative. Looks like it's a quotient rule. Low d high minus high d low over the bottom square. Simplify it a little bit. Looks like we get x plus 2 minus x over x plus 2 squared. Cancel the x's. My first derivative is 2 over x plus 2 squared. All right, so it's asking where on the graph does the graph have a slope or derivative that equals this. So it's literally asking where does the derivative equal 1/2 at what x values. So take the derivative and set it equal to 1/2. I'll put it down here. Take the derivative and set it equal to 1/2 and solve, and you're done. So cross multiply. Looks like we get 4 equals x plus 2 squared. By the way, you see that some of these answers have 2 coordinates. That's because when you take the square root, you get plus or minus 2. And then we can subtract 2 to both. So it looks like we get 2 answers. X equals, if it was a positive 2, we'd get 0. If it was a negative 2, we'd get x equals -4. So x equals 0, x equals -4. I imagine it's this one. They're giving you the y coordinate because they want you to plug it back in and make sure it works. When I plug in 0 to the original, I get 0, so that works. When I plug in -4 to the original, I get -4 over -4 plus 2 is -2, which is 2. So that worked too. Okay. So this is one that sounds a little bizarre because they threw the word property at you. Oh my gosh, property. But they're just saying, where does this function have a slope of 1/2? So you got to take the derivative, which means slope, and set it equal to 1/2. And not a hard one. It was only number 19 on this practice, which means it's towards the end. Not well. There's this whole. I think this one had 25. Oh, no, it had 30. So yeah, this is had 28. So typically the AP test gets harder as you go. FYI. All right, so if you were able to do that one, cool. We'll keep doing this where I'll have ones at the end that you can kind of look through and practice. Today, here's just one. There are other ones, but I'm tempted to do 2. But no, we'll leave it at 1 for now. I think that's fine. We'll leave it at 1 for now. In the discussion, you can tell me if you want more of these. All right, that's it.